Welcome back. In our last video, we started a new example where you took a pop quiz that you didn't know the questions to, and we determined that the random variable in this 10-question blind pop quiz was the number of correct answers that you got out of 10. And it might be interesting if you did that. If you haven't, record how many that you got right, just so you can compare to what we're going to be talking about a little later. And we also determined that we can use the binomial model to calculate probabilities of getting certain numbers of questions correct. Essentially, we're saying this is a binomial random variable. And we determined that by checking all the conditions that we have Bernoulli trials. We've got two outcomes. Success or failure in this case is either getting a question right or wrong. The same probability for each trial, we have that. You had a 20% chance of getting each one of these questions correct, and each question, whether you got it right or wrong, was independent of all the others. Right, so we're going to be using a binomial model here. So now part B, we want to name the distribution. We already know it's binomial, and determine its parameters. So we know that the random variable x is binomial. The parameters, the only parameters for a binomial model are the number of trials and the probability of success. That's n and p. So n, the number of trials here, we already established in the last video, a trial is a single question, so we've got 10 of those. And the probability of success, we already established that as well. It's 0.2 for each question. So that is, the distribution is binomial, and the parameters n and p. Part C. It says, what is the probability of getting exactly 2 questions correct on the quiz? Maybe you got exactly 2 questions correct. And we already established that the probability of success is 0.2, so it might make sense that this is a relatively common result. But how likely is it? I want you to use what you know to try and answer this question on your own before we talk about it together. So pause the video, come back when you've got it. Nice review of what we learned in the last video here. We want the probability that x is exactly 2. This is how we write the probability of getting exactly 2 questions correct on the quiz. And I've written both versions of what you can write to get full credit here. You can use binom PDF with n equals 10, p equals 0.2, and x equals 2. Or you can use the binomial probability formula, 10 choose 2 times 0.2 squared times 0.8 to the 10 minus 2 power. Either way, you should get 0.3020, or about 30.2%. So even though we might expect that this is a fairly common occurrence, it really is only about 30% of the time. Only about 3 out of every 10 students that take this blind pop quiz are going to get exactly 2 questions correct. Part D, next question. How likely is it for a random student to get no more than 4 questions correct? Okay. It's important to know that there are several different ways that questions can be phrased that ask the same type of question. So you might notice this doesn't ask what the probability is of getting no more than 4 questions correct. But that is what this is saying. It's just a different way of phrasing it. How likely is it for a random student to do something is the same as what is the probability of it. So go ahead and tackle this one. Again, it's a review from the last video. Come back when you've got it. For this one, we want to know the probability that x is less than or equal to 4. So if you have the wrong inequality symbol here, if you had a less than, then that just shows that you need to maybe pay a little more attention to the verbiage of what the question is asking. No more than 4, does that include 4? Yes. No more than 4 is anything up to and including 4. So that's less than or equal to 4. You could have written less than 5 here. And the beauty of it is, that would be the same thing here. Whether this is less than or equal to 4 or less than 5, you're using binom CDF with these parameters, right? So again, you can use Binomial CDF. I would highly encourage you to calculate the probability that way. You could also write out the binomial probability formula this way. I would not write all 5 terms of that. No one wants to see that. Plus, the chances that you make one tiny little transcription error might be pretty high there. So you only would have to write the first term, ... and the last term, right? Making sure you add them all. Okay, and that's starting with 0 successes going all the way up to 4. But again, this is acceptable as long as you remember to write your parameters here. What do each of the numbers represent? Number of trials, probability of success, highest number of successes we're looking at. That gives you 0.9672. So you're almost certain to get no more than 4 questions correct on this quiz if you're guessing at random. So if you got more than 4, congratulations, you're in the 3.28% to get more than 4 right. So I've got one more question for you. Last question of this setup. To pass the quiz, more than 5 correct answers are needed, right? You need more than 5 of these correct to pass the quiz, to get at least a passing grade. What is the probability of a random student passing the quiz? The way that you took it, where you're essentially just guessing the right answers. What is the probability of a random student passing the quiz? This is the last one. See if you can get this. This part had the most intricacy of what you needed to do to get the correct answer. This is the probability that x is greater than 5, or the probability that x is greater than or equal to 6. You could have written it that way also. So I like to turn any probability statement that has a greater than or equal to sign and write the complement right away. Instead of going into Binomial PDF or CDF, just to make sure I'm putting the right number in there, I like writing the complement. So the probability that x is greater than 5 is the same thing as 1 minus the probability that x is less than or equal to 5. And the reason I like writing this as less than or equal to a number is that when I turn this into Binomial CDF, I know I can use whatever this number is. If I had written this as 1 minus the probability that x is less than 6, then this would still be x equals 5, but then I'd have to do some extra mental gymnastics to make sure I had the right number there. So that's a good trick. If you've got a greater than or equal to sign here, if that's what it's looking for, write the complement first, then write it in terms of Binomial CDF, right? So that's this. Remember to type your 1 minus before you do the Binomial CDF, or you're going to get the complement of what you should. This is what it looks like if you write the binomial probability formula. Again, I don't recommend that. As long as you label each of your parameters here with the calculator speak, that's going to be good enough. And it certainly doesn't take nearly as long or nearly as much bandwidth in your brain to write this. And either way, though, you should get 0.0064. This is how I determine if students are actually trying when they take tests. Because if you don't pass, chances are you were guessing. Students who are guessing don't tend to pass on multiple choice tests. Less than 1% of students would pass this quiz just by guessing. So hopefully by this point, now that we've seen 2 complete examples, you should be more comfortable being able to define a binomial random variable by checking the conditions to see if you've got Bernoulli trials, and calculating any probability based on a certain number of trials n and a probability of success p. I want to continue with the random pop quiz example, but again, I had every student do this, and let's suppose I want to know what the mean is of all the students who took this quiz. Or really the mean of the population of all possible students who could have taken that quiz. How many questions would we expect people to get right on average when they do this? You might already have an idea. And maybe you're right. But let's see if we can use statistics to try and confirm what you might be thinking here. So let's try to find the mean. Right, so this is our question. We want to know the mean number of questions out of 10 we can expect a random student to get correct. And as usual, I'm not going to give you the formula for the mean of a binomial random variable. We're going to try and figure it out ourselves, because I think you know what it is. If we were in class, in person, I would just ask this, and somebody would probably give an answer, like 2. And I'd be like, why? And hopefully they would explain, or somebody would be able to figure out why that is. But let's just walk through it. There are 10 questions, and the probability that you get any individual question right is 0.2. So doesn't it stand to reason that if you get 0.2 of the 10 questions correct, on average, that would be 2? That's exactly how it works. So we want to know the mean of the population. So we're going to use the correct notation. The population mean of the random variable x, where x represents the number of questions correct out of 10, that's going to be equal to, in this particular case, 10, because there are 10 questions, times 0.2, the probability of success. And that equals 2, which is correct. So, we know that x, this random variable, is a binomial random variable. We proved that in part A of the last example. So, we can generalize this idea to find the mean of any binomial random variable with any number of trials and any probability of success. It's that simple. It's n times p. That's all it is. So if I gave you a 40-question quiz and the probability of you getting the right answer was 0.5, you would expect to get 40 times 0.5, or 20 of those 40 questions right, if it was like true, false, or something. It's that easy. Not all formulas have to be complicated. Some you can actually reason to make sense, like this one here. So even if you forgot this formula, if you were asked what the mean was for a particular binomial random variable, I have confidence that you could come up with it on your own. Now, the next question might not be so simple. This one is going to be a little more difficult. What about the standard deviation? So that is the standard deviation of a binomial random variable. It's the square root of n times p times 1 minus p. Getting there was a little iffy. Again, you will never have to go through this process on your own. And in fact, this formula and this formula are on the AP test formula sheet. So you will have access to these formulas, even on the AP test. You do not have to memorize them. All you need to know is if you know you have a binomial random variable, either you've checked conditions and you know there are Bernoulli trials, or the problem tells you that x is a binomial random variable. If you want the mean of that variable, it's n times p. If you need the standard deviation of that variable, it's the square root of n times p times 1 minus p. So I'll get out of the way here. If you want to pause the video and write all that down, you can, but I just don't want you to think that these came from nowhere. They are derived in this way, but you're never going to have to derive them on your own. You're just going to use them to answer questions about the mean and standard deviation of a binomial random variable, like this. So I just want to use these formulas and make sure you know how to utilize them. So let's go back to our cereal box athlete example. Halep is on 30% of boxes. What are the mean and standard deviation of the number of Haleps we can expect to see in 25 boxes? You don't need to remember anything else from the example. All the information you need is here. Because remember, all you need to calculate the mean and standard deviation are n and p. And you've got both of those here. So go ahead real quick, calculate the mean and standard deviation just so we know what we're doing, and then we'll move on. So just using these formulas, plugging in our numbers for n and p, we get a mean of 7.5 Haleps and a standard deviation of 2.29 Haleps. So in 25 boxes, if we open 25 boxes once, obviously we're not going to get 7.5 Haleps. That's impossible. It has to be a whole number. This represents what we would see on average if we kept taking samples of 25 boxes forever, right? Sometimes you get 7, sometimes you get 12, sometimes you might not get any, but on average it's 7.5. And the standard deviation, how many hallops do we expect to vary from this mean on average? About 2.29. So if we were to only get like 1 or 2 hallops, that'd be really unusual because it's more than 2 standard deviations from the mean, for example. I was originally planning to get a little further in this video and only have 1 more before the unit test, but it turns out there are going to be 2 more videos in this unit before the end. So you should probably start looking at the last couple progress checks for Unit 4 if you haven't already, multiple choice part C, and the free response questions. It's possible that there are still some things that we haven't covered that are in those progress checks, but you can probably do most of it. So if there's a way for you to start and have it save your progress so that you can come back to it later, I would recommend doing that. The Chapter 16 homework will be due after the last video, so there will still be a couple more. But again, there are probably a lot of things on that homework assignment that you can do at this point. So I would recommend looking at that, seeing if you can do some of at least the first few problems. As always, if you have any questions on any of those things, let me know. Shoot me an email. More than happy to help. But I think that's it for this one. So I will see you in the next video.